The history of special relativity consists of many theoretical results and empirical findings obtained by Albert A. Michelson, Hendrik Lorentz, Henry Poincaré, and others. It culminated in the theory of special relativity proposed by Albert Einstein, and subsequent work of Max Planck, Hermann Minkowski, and others. Introduction. Although Isaac Newton based his physics on absolute time and space, he also adhered to the principle of relativity of Galileo Galilei. This can be stated as far as the laws of mechanics are concerned, all observers in inertial motion are equally privileged, and no preferred state of motion can be attributed to any particular inertial observer. However, as to electromagnetic theory and electrodynamics, during the 19th century the wave theory of light as a disturbance of a light medium or luminiferous ether was widely accepted, the theory reaching its most developed form in the work of James Clerk Maxwell. According to Maxwell's theory, all optical and electrical phenomena propagate through a light medium, or luminiferous ether, which suggested that it should be possible to experimentally determine motion relative to the ether. The failure of any known experiment to detect motion through the ether led Hendrik Lorentz, starting in 1892, to develop a theory of electrodynamics based on an immobile non-material luminiferous ether, physical length contraction, and a local time, in which Maxwell's equations retain their form in all inertial frames of reference. Working with Lorentz's ether theory, Henry Poincaré, having earlier proposed the relativity principle as a general law of nature, including electrodynamics and gravitation, used this principle in 1905 to correct Lorentz's preliminary transformation formulas, resulting in an exact set of equations that are now called the Lorentz transformations. A little later in the same year Albert Einstein published his original paper on special relativity, in which, again based on the relativity principle, he independently derived and radically reinterpreted the Lorentz transformations by changing the fundamental definitions of space and time intervals while abandoning the absolute simultaneity of Galilean kinematics, thus avoiding the need for any reference to a luminiferous ether in classical electrodynamics. Subsequent work of Hermann Minkowski, in which he introduced a four-dimensional geometric spacetime model for Einstein's version of special relativity, paved the way for Einstein's later development of his general theory of relativity, and laid the foundations of relativistic field theories. Ether and electrodynamics of moving bodies. Ether models and Maxwell's equations. Following the work of Thomas Young, 1804, and Augustin Jean Fresnel, 1816, it was believed that light propagates as a transverse wave within an elastic medium called luminiferous ether. However, a distinction was made between optical and electrodynamical phenomena, so it was necessary to create specific ether models for all phenomena. Attempts to unify those models, or to create a complete mechanical description of them, did not succeed, but after considerable work by many scientists, including Michael Faraday and Lord Kelvin, James Clerk Maxwell, 1864, developed an accurate theory of electromagnetism by deriving a set of equations in electricity, magnetism, and inductance, named Maxwell's equations. He first proposed that light was in fact undulations, electromagnetic radiation, in the same ethereal medium that is the cause of electric and magnetic phenomena. However, Maxwell's theory was unsatisfactory regarding the optics of moving bodies, and while he was able to present a complete mathematical model, he was not able to provide a coherent mechanical description of the ether. After Heinrich Hertz in 1887 demonstrated the existence of electromagnetic waves, Maxwell's theory was widely accepted. In addition, Oliver Heaviside and Hertz further developed the theory and introduced modernized versions of Maxwell's equations. The Maxwell-Hertz or Heaviside-Hertz equation subsequently formed an important basis for the further development of electrodynamics, and Heaviside's notation is still used today. Other important contributions to Maxwell's theory were made by George Fitzgerald, Joseph John Thomson, John Henry Poynting, Hendrik Lorentz, and Joseph Lorrimore. Search for the ether. Regarding the relative motion and the mutual influence of matter and ether, there were two controversial theories. One of them was developed by Fresnel, and subsequently Lorentz. This model, stationary ether theory, supposed that light propagates as a transverse wave and ether is partially dragged with a certain coefficient by matter. Based on this assumption, Fresnel was able to explain the aberration of light and many optical phenomena. The other hypothesis was proposed by George Gabriel Stokes, who stated in 1845 that the ether was fully dragged by matter. Later this view was also shared by Hertz. In this model the ether might be, by analogy with pine pitch, rigid for fast objects and fluid for slower objects. Thus the Earth could move through it fairly freely, but it would be rigid enough to transport light. Fresnel's theory was preferred because his dragging coefficient was confirmed by the Fizeau experiment in 1851, who measured the speed of light in moving liquids. A. Michelson. Albert A. Michelson, 1881, tried to measure the relative motion of the Earth and ether wind, as it was expected in Fresnel's theory, by using an interferometer. He could not determine any relative motion, so he interpreted the result as a confirmation of the thesis of Stokes. However, Lorentz, 1886, showed Michelson's calculations were wrong and that he overestimated the accuracy of the measurement. This, together with a large margin of error, made the result of Michelson's experiment inconclusive. In addition, Lorentz showed that Stokes' completely dragged ether led to contradictory consequences, and therefore he supported an ether theory similar to Fresnel's. To check Fresnel's theory again, Michelson and Edward W. Morley, 1886, performed a repetition of the Fizeau experiment. Fresnel's dragging coefficient was confirmed very exactly on that occasion, and Michelson was now of the opinion that Fresnel's stationary ether theory was correct. To clarify the situation, Michelson and Morley, 1887, repeated Michelson's 1881 experiment, and they substantially increased the accuracy of the measurement. However, this now famous Michelson-Morley experiment again yielded a negative result, i.e., no motion of the apparatus through the ether was detected, although the Earth's velocity is 60 km/s different in winter than summer. So the physicists were confronted with two seemingly contradictory experiments, the 1886 experiment, as an apparent confirmation of Fresnel's stationary ether, and the 1887 experiment, as an apparent confirmation of Stokes' completely dragged ether. A possible solution to the problem was shown by Waldemar Voigt, 1887, who investigated the Doppler effect for waves propagating in an incompressible elastic medium, and deduced transformation relations that left the wave equation in free space unchanged, and explained the negative result of the Michelson-Morley experiment. The Voigt transformations include the Lorentz factor for the y and z coordinates, and a new time variable which later was called local time. However, Voigt's work was completely ignored by his contemporaries. Fitzgerald, 1889, offered another explanation of the negative result of the Michelson-Morley experiment. Contrary to Voigt, he speculated that the intermolecular forces are possibly of electrical origin so that material bodies would contract in the line of motion, length contraction. This was in connection with the work of Heaviside, 1887, who determined that the electrostatic fields in motion were deformed, Heaviside ellipsoid, which leads to physically undetermined conditions at the speed of light. However, Fitzgerald's idea remained widely unknown, and was not discussed before Oliver Lodge published a summary of the idea in 1892. Also Lorentz, 1892b. proposed length contraction independently from Fitzgerald in order to explain the Michelson-Morley experiment. For plausibility reasons, Lorentz referred to the analogy of the contraction of electrostatic fields. However, even Lorentz admitted that that was not a necessary reason, and length contraction consequently remained an ad hoc hypothesis. Lorentz's theory of electrons. Hendrik Antoon Lorentz. Lorentz, 1892, set the foundations of Lorentz ether theory by assuming the existence of electrons which he separated from the ether, and by replacing the Maxwell-Hertz equations by the Maxwell-Lorentz equations. In his model, the ether is completely motionless and, contrary to Fresnel's theory, also is not partially dragged by matter. An important consequence of this notion was that the velocity of light is totally independent of the velocity of the source. Lorentz gave no statements about the mechanical nature of the ether and the electromagnetic processes, but, vice versa, tried to explain the mechanical processes by electromagnetic ones and therefore created an abstract electromagnetic ether. In the framework of his theory, Lorentz calculated, like Heaviside, the contraction of the electrostatic fields. Lorentz, 1895, also introduced what he called the theorem of corresponding states for terms of first order in. This theorem states that a moving observer, relative to the ether in his fictitious field, makes the same observations as a resting observer in his real field. An important part of it was local time, which paved the way to the Lorentz transformation, and which he introduced independently of Voigt. With the help of this concept, Lorentz could explain the aberration of light, the Doppler effect, and the Fizeau experiment as well. However, Lorentz's local time was only an auxiliary mathematical tool. To simplify the transformation from one system into another, it was Poincaré, in 1900, who recognized that local time is actually indicated by moving clocks. Lorentz also recognized that his theory violated the principle of action and reaction, since the ether acts on matter, but matter cannot act on the immobile ether. A very similar model was created by Joseph Larmor, 1897-1900. Larmor was the first to put Lorentz's 1895 transformation into a form algebraically equivalent to the modern Lorentz transformations. However, he stated that his transformations preserve the form of Maxwell's equations only to second order of. Lorentz later noted that these transformations did in fact preserve the form of Maxwell's equations to all orders of. Larmor noticed on that occasion that not only can length contraction be derived from it, but he also calculated some sort of time dilation for electron orbits. Larmor specified his considerations in 1900 and 1904. Independently of Larmor, also Lorentz, 1899, extended his transformation for second-order terms and noted a mathematical time dilation effect as well. Other physicists besides Lorentz and Larmor also tried to develop a consistent model of electrodynamics. For example, Emil Cohn, 1900-1901, created an alternative electrodynamics, in which he, as one of the first, discarded the existence of the ether, at least in the previous form, and would use, like Ernst Mach, the fixed stars, as a reference frame instead. Due to inconsistencies within his theory, like different light speeds in different directions, it was superseded by Lorentz's and Einstein's. Electromagnetic mass. During his development of Maxwell's theory, J. Thomson, 1881, recognized that charged bodies are harder to set in motion than uncharged bodies. He also noticed that the mass of a body in motion is increased by a constant quantity. Electrostatic fields behave as if they add an electromagnetic mass to the mechanical mass of the bodies. I.e., according to Thomson, electromagnetic energy corresponds to a certain mass. This was interpreted as some form of self-inductance of the electromagnetic field. Thomson's work was continued and perfected by Fitzgerald, Heaviside, 1888, and George Frederick Charles Searle, 1896. 1897. For the electromagnetic mass they gave in modern notation the formula, where is the electromagnetic mass, and is the electromagnetic energy. Heaviside and Searle also recognized that the increase of the mass of a body is not constant, and varies with its velocity. Consequently, Searle noted the impossibility of superluminal velocities, because infinite energy would be needed to exceed the speed of light. Also for Lorentz, 1899, the integration of the speed dependence of masses recognized by Thomson was especially important. He noticed that the mass not only varied due to speed, but is also dependent on the direction, and he introduced what Abraham later called longitudinal and transverse mass. The transversal mass corresponds to what later was called relativistic mass. Wilhelm Wien, 1900, assumed, following the works of Thomson, Heaviside, and Searle, that the entire mass is of electromagnetic origin, which was formulated in the context that all forces of nature are electromagnetic ones, the electromagnetic worldview. Wien stated that, if it is assumed that gravitation is an electromagnetic effect too, then there has to be a proportionality between electromagnetic energy, inertial mass, and gravitational mass. In the same paper, Henry Poincaré, 1900b, found another way of combining the concepts of mass and energy. He recognized that electromagnetic energy behaves like a fictitious fluid with mass density of, and defined a fictitious electromagnetic momentum as well. However, he arrived at a radiation paradox which was fully explained by Einstein, in 1905. Walter Kaufmann, 1901-1903, was the first to confirm the velocity dependence of electromagnetic mass by analyzing the ratio, whereas the charge and the mass of cathode rays. He found that the value of decreased with the speed, showing that, assuming the charge constant, the mass of the electron increased with the speed. He also believed that those experiments confirmed the assumption of Wien, that there is no real mechanical mass, but only the apparent electromagnetic mass, or in other words, the mass of all bodies is of electromagnetic origin. Max Abraham, 1902-1904, who was a supporter of the electromagnetic worldview, quickly offered an explanation for Kaufmann's experiments by deriving expressions for the electromagnetic mass together. With this concept, Abraham introduced, like Poincaré, in 1900, the notion of electromagnetic momentum, which is proportional to. But unlike the fictitious quantities introduced by Poincaré, he considered it as a real physical entity. Abraham also noted, like Lorentz in 1899, that this mass also depends on the direction, and coined the names longitudinal and transverse mass. In contrast to Lorentz, he didn't incorporate the contraction hypothesis into his theory, and therefore his mass terms differed from those of Lorentz. Based on the preceding work on electromagnetic mass, Friedrich Hasen-Oerl suggested that part of the mass of a body, which he called apparent mass, can be thought of as radiation bouncing around a cavity. The apparent mass of radiation depends on the temperature, because every heated body emits radiation, and is proportional to its energy. Hasen-Oerl stated that this energy-apparent mass relation only holds as long as the body radiates, i.e., if the temperature of a body is greater than 0 K. At first he gave the expression for the apparent mass. However, Abraham and Hasen-Oerl himself in 1905 changed the result to the same value as for the electromagnetic mass for a body at rest. Absolute space and time. Some scientists and philosophers of science were critical of Newton's definitions of absolute space and time. Ernst Mach, 1883, argued that absolute time and space are essentially metaphysical concepts, and thus scientifically meaningless, and suggested that only relative motion between material bodies is a useful concept in physics. Mach argued that even effects that according to Newton depend on accelerated motion with respect to absolute space, such as rotation, could be described purely with reference to material bodies, and that the inertial effects cited by Newton in support of absolute space might instead be related purely to acceleration with respect to the fixed stars. Carl Newman, 1870, introduced a body alpha which represents some sort of rigid and fixed body for defining inertial motion. Based on the definition of Newman, Heinrich Steinitz, 1883, argued that, if gyroscopes don't measure any signs of rotation, then one can speak of inertial motion which is related to a fundamental body, and a fundamental coordinate system. Eventually, Ludwig Lang, 1885, was the first to coin the expression inertial frame of reference and inertial timescale as operational replacements for absolute space and time. He defined inertial frame as a reference frame in which a mass point thrown from the same point in three different, non-coplanar directions follows rectilinear paths each time it is thrown. In 1902, Henry Poincaré published a collection of essays titled Science and Hypothesis, which included detailed philosophical discussions on the relativity of space, time, and on the conventionality of distant simultaneity, the conjecture that a violation of the relativity principle can never be detected, the possible non-existence of the ether, together with some arguments supporting the ether, and many remarks on non-Euclidean versus Euclidean geometry. There were also some attempts to use time as a fourth dimension. This was done as early as 1754 by Jean-Léon d'Alembert in the Encyclopédie, and by some authors in the 19th century, like H. G. Wells in his novel The Time Machine, 1895. In 1901 a philosophical model was developed by Minihert Palagi, in which space and time were only two sides of some sort of space-time. He used time as an imaginary fourth dimension, which he gave the form where, i.e., imaginary number. However, Palagi's time coordinate is not connected to the speed of light. He also rejected any connection with the existing constructions of n-dimensional spaces and non-Euclidean geometry, so his philosophical model bears only little resemblance with space-time physics, as it was later developed by Minkowski. Light constancy and the principle of relative motion. Henry Poincaré. In the second half of the 19th century, there were many attempts to develop a worldwide clock network synchronized by electrical signals. On that occasion, the finite propagation speed of light had to be considered as well. So Henry Poincaré, 1898, in his paper The Measure of Time drew some important consequences of this process, and explained that astronomers, in determining the speed of light, simply assume that light has a constant speed, and that this speed is the same in all directions. Without this postulate it would be impossible to infer the speed of light from astronomical observations, as Lorentz did based on observations of the moons of Jupiter. Poincaré also noted that the propagation speed of light can be, and in practice often is, used to define simultaneity between spatially separate events. He concluded by saying that the simultaneity of two events, or the order of their succession, the equality of two durations, are to be so defined that the enunciation of the natural laws may be as simple as possible. In other words, all these rules, all these definitions are only the fruit of an unconscious opportunism. In some other papers, Poincaré, 1895-1900b, argued that experiments like that of Michelson-Morley show the impossibility of detecting the absolute motion of matter, i.e., the relative motion of matter in relation to the ether. He called this the principle of relative motion. In the same year he interpreted Lorentz's local time as the result of a synchronization procedure based on light signals. He assumed that two observers A and B, which are moving in the ether, synchronize their clocks by optical signals. Since they believe themselves to be at rest, they must consider only the transmission time of the signals, and then cross-reference their observations to examine whether their clocks are synchronous. However, from the point of view of an observer at rest in the ether, the clocks are not synchronous, and indicate the local time. But because the moving observers do not know anything about their movement, they do not recognize this. So, contrary to Lorentz, Poincaré defined local time can be measured and indicated by clocks. Therefore, in his recommendation of Lorentz for the Nobel Prize in 1902, Poincaré argued that Lorentz has convincingly explained the negative outcome of the ether drift experiments by inventing the diminished time, i.e., that two events at different places could appear as simultaneous, although they are not simultaneous in reality. Like Poincaré, Alfred Butcherer, 1903, believed in the validity of the relativity principle within the domain of electrodynamics, but contrary to Poincaré, Butcherer even assumed that this implies the non-existence of the ether. However, the theory that was created by him later in 1906 was incorrect and not self-consistent, and the Lorentz transformation was absent within his theory as well. Lorentz's 1904 model. In his paper Electromagnetic Phenomena in a System Moving with Any Velocity Smaller Than That of Light, Lorentz, 1904, was following the suggestion of Poincaré and attempted to create a formulation of electrodynamics, which explains the failure of all known ether drift experiments, i.e. the validity of the relativity principle. He tried to prove the applicability of the Lorentz transformation for all orders, although he didn't succeed completely. Like Wien and Abraham, he argued that there exists only electromagnetic mass, not mechanical mass, and derived the correct expression for longitudinal and transverse mass, which were in agreement with Kaufmann's experiments, even though those experiments were not precise enough to distinguish between the theories of Lorentz and Abraham. And using the electromagnetic momentum, he could explain the negative result of the Trout and Noble experiment, in which a charged parallel plate capacitor moving through the ether should orient itself perpendicular to the motion. Also, the experiments of Rayleigh and Brace could be explained. Another important step was the postulate that the Lorentz transformation has to be valid for non-electrical forces as well. At the same time, when Lorentz worked out his theory, Wien, 1903, recognized an important consequence of the velocity dependence of mass. He argued that superluminal velocities were impossible, because that would require an infinite amount of energy. The same was already noted by Thomson, 1893, and Searle, 1897. And in June 1904, after he had read Lorentz's 1904 paper, he noticed the same in relation to length contraction, because at superluminal velocities the factor becomes imaginary. Lorentz's theory was criticized by Abraham, who demonstrated that on one side the theory obeys the relativity principle, and on the other side the electromagnetic origin of all forces is assumed. Abraham showed that both assumptions were incompatible, because in Lorentz's theory of the contracted electrons, non-electric forces were needed in order to guarantee the stability of matter. However, in Abraham's theory of the rigid electron, no such forces were needed. Thus the question arose whether the electromagnetic conception of the world, compatible with Abraham's theory, or the relativity principle, compatible with Lorentz's theory, was correct. In a September 1904 lecture in St. Louis named Principles of Mathematical Physics, Poincaré drew some consequences from Lorentz's theory, and defined, in modification of Galileo's relativity principle and Lorentz's theorem of corresponding states, the following principle: the principle of relativity, according to which the laws of physical phenomena must be the same for a stationary observer, as for one carried along in a uniform motion of translation, so that we have no means, and can have none, of determining whether or not we are being carried along in such a motion. He also specified his clock synchronization method, and explained the possibility of a new method, or new mechanics, in which no velocity can surpass that of light for all observers. However, he critically noted that the relativity principle, Newton's action and reaction, the conservation of mass, and the conservation of energy are not fully established, and are even threatened by some experiments. Also Emil Cohn, 1904, continued to develop his alternative model, as described above, and while comparing his theory with that of Lorentz, he discovered some important physical interpretations of the Lorentz transformations. He illustrated, like Joseph Larmor, in the same year, this transformation, by using rods and clocks. If they are at rest, in the ether, they indicate the true length and time, and if they are moving, they indicate contracted and dilated values. Like Poincaré, Cohn defined local time as the time which is based on the assumption of isotropic propagation of light. Contrary to Lorentz and Poincaré, it was noticed by Cohn that within Lorentz's theory the separation of real and apparent coordinates is artificial, because no experiment can distinguish between them. Yet according to Cohn's own theory, the Lorentz transformed quantities would only be valid for optical phenomena, while mechanical clocks would indicate the real time. Poincaré's dynamics of the electron. On June 5, 1905, Henri Poincaré submitted the summary of a work which closed the existing gaps of Lorentz's work. This short paper contained the results of a more complete work which would be published later, in January 1906. He showed that Lorentz's equations of electrodynamics were not fully Lorentz covariant. So he pointed out the group characteristics of the transformation, and he corrected Lorentz's formulas for the transformations of charge density and current density, which implicitly contained the relativistic velocity addition formula, which he elaborated in May in a letter to Lorentz. Poincaré used for the first time the term Lorentz transformation, and he gave the transformations their symmetrical form used to this day. He introduced a non-electrical binding force, the so-called Poincaré stresses, to ensure the stability of the electrons and to explain length contraction. He also sketched a Lorentz invariant model of gravitation, including gravitational waves, by extending the validity of Lorentz invariance to non-electrical forces. Eventually Poincaré, independently of Einstein, finished a substantially extended work of his June paper. The so-called Palermo paper received July 23, printed December 14, published January 1906. He spoke literally of the postulate of relativity. He showed that the transformations are a consequence of the principle of least action, and developed the properties of the Poincaré stresses. He demonstrated in more detail the group characteristics of the transformation, which he called the Lorentz group, and he showed that the combination is invariant. While elaborating his gravitational theory, he said the Lorentz transformation is merely a rotation in four-dimensional space about the origin, by introducing as a fourth imaginary coordinate, contrary to Poincaré, he included the speed of light, and he already used four vectors. He wrote that the discovery of magneto-cathode rays by Paul Ulrich Villard, 1904, seemed to threaten the entire theory of Lorentz, but this problem was quickly solved. However, although in his philosophical writings Poincaré rejected the ideas of absolute space and time, in his physical papers he continued to refer to an undetectable ether. He also continued, 1900b, 1904, 1906, 1908b, to describe coordinates and phenomena as local/apparent, for moving observers, and true/real, for observers at rest in the ether. So, with a few exceptions, most historians of science argue that Poincaré did not invent what is now called special relativity, although it is admitted that Poincaré anticipated much of Einstein's methods and terminology. Special relativity. Einstein 1905. Electrodynamics of moving bodies. Albert Einstein, 1921. On September 26, 1905, received June 30, Albert Einstein published his Annus Mirabilis paper on what is now called special relativity. Einstein's paper includes a fundamental new definition of space and time. All time and space coordinates and all reference frames are equal, so there is no true or apparent time, and makes the ether an unnecessary concept. He identified two fundamental principles, the principle of relativity and the principle of the constancy of light, which served as the axiomatic basis of his theory. To better understand Einstein's step, a summary of the situation before 1905, as it was described above, shall be given. It must be remarked that Einstein was familiar with the 1895 theory of Lorentz and Science and Hypothesis by Poincaré, but not their papers of 1904 to 1905. A. Maxwell's electrodynamics, as presented by Lorentz in 1895, was the most successful theory at this time. Here, the speed of light is constant in all directions in the stationary ether and completely independent of the velocity of the source. B. The inability to find an absolute state of motion, i.e. the validity of the relativity principle, as the consequence of the negative results of all ether drift experiments and effects, like the moving magnet and conductor problem, which only depend on relative motion. C. The Fizeau experiment. D. The aberration of light. With the following consequences for the speed of light, and the theories known at that time. 1. The speed of light is not composed of the speed of light in vacuum, and the velocity of a preferred frame of reference, by B. This contradicts the theory of the nearly stationary ether. 2. The speed of light is not composed of the speed of light in vacuum, and the velocity of the light source, by A and C. This contradicts the emission theory. 3. The speed of light is not composed of the speed of light in vacuum and the velocity of an ether that would be dragged within or in the vicinity of matter by a c and d. This contradicts the hypothesis of the complete ether drag. 4. The speed of light in moving media is not composed of the speed of light when the medium is at rest and the velocity of the medium, but is determined by Fresnel's dragging coefficient by C West 1. To make the preceding theories tenable, the introduction of ad hoc hypotheses would be required. Yet in science the assumption of a conspiracy of effects which prevent the discovery of other effects is considered to be very improbable, and it would violate Occam's razor as well. So Einstein refused to invent auxiliary hypotheses and drew the direct conclusions from the facts stated above, that the relativity principle is correct and the speed of light is constant in all inertial reference frames. Because of his axiomatic method, Einstein was able to derive all results of his predecessors, and in addition the formulas for the relativistic Doppler effect and relativistic aberration on a few pages, while his predecessors needed years of long, complicated work to arrive at the same mathematical formalism. Lorentz and Poincaré had also adopted these same principles as necessary to achieve their final results, but didn't recognize that they were also sufficient, and hence they obviated all the other assumptions, especially the stationary ether, underlying Lorentz's initial derivations. Another reason for Einstein's rejection of the ether was probably his work on quantum physics. Einstein found out that light can also be described as a particle, so the ether as the medium for electromagnetic waves, which was highly important for Lorentz and Poincaré, had no place in his theoretical concepts anymore. It's notable that Einstein's paper contains no direct references to other papers. However, many historians of science, like Holton, Miller, Stackel, have tried to find out possible influences on Einstein. He stated that his thinking was influenced by the empiricist philosophers David Hume and Ernst Mach. Regarding the relativity principle, the moving magnet and conductor problem, possibly after reading a book of August Föppel, and the various negative ether drift experiments were important for him to accept that principle, but he denied any significant influence of the most important experiment, the Michelson-Morley experiment. Other possible sources are Poincaré's Science and Hypothesis, where he described the principle of relativity, and which was read by Einstein in 1904, and the writings of Max Abraham, from whom he borrowed the terms Maxwell-Hertz equations, and longitudinal and transverse mass. Regarding his views on electrodynamics, and the principle of the constancy of light, Einstein stated that Lorentz's theory of 1895, or the Maxwell-Lorentz electrodynamics, and also the Fizeau experiment had considerable influence on his thinking. He said in 1909 and 1912 that he borrowed that principle from Lorentz's stationary ether, which implies validity of Maxwell's equations and the constancy of light in the ether frame, but he recognized that this principle together with the principle of relativity makes the ether useless. As he wrote in 1907, and in later papers, the apparent contradiction between those principles can be solved if it is realized that Lorentz's local time is not an auxiliary quantity, but can simply be defined as time, and is connected with signal velocity. Before Einstein, also Poincaré developed a similar physical interpretation of local time, and noticed the connection to signal velocity, but contrary to Einstein he continued to argue that clocks in the ether show the true time, and moving clocks show the apparent time. Eventually, in 1953 Einstein described the advances of his theory, although Poincaré already stated in 1905 that Lorentz invariance is a general condition for any physical theory. There is no doubt that the special theory of relativity, if we regard its development in retrospect, was ripe for discovery in 1905. Lorentz had already recognized that the transformations named after him are essential for the analysis of Maxwell's equations, and Poincaré deepened this insight still further. Concerning myself, I knew only Lorentz's important work of 1895, but not Lorentz's later work, nor the consecutive investigations by Poincaré. In this sense my work of 1905 was independent. The new feature of it was the realization of the fact that the bearing of the Lorentz transformation transcended its connection with Maxwell's equations, and was concerned with the nature of space and time in general. A further new result was that the Lorentz invariance is a general condition for any physical theory. This was for me of particular importance, because I had already previously found that Maxwell's theory did not account for the microstructure of radiation, and could therefore have no general validity. Mass-energy equivalence. Mass-energy equivalence, history. Already in 10 of his paper on electrodynamics, Einstein used the formula for the kinetic energy of an electron. In elaboration of this he published a paper, received September 27, November 1905, in which Einstein showed that when a material body lost energy, either radiation or heat, of amount T, its mass decreased by the amount T/c2. This led to the famous mass-energy equivalence formula, E equals mc2. Einstein considered the equivalency equation to be of paramount importance, because it showed that a massive particle possesses an energy, the rest energy distinct from its classical kinetic and potential energies. As it was shown above, many authors before Einstein arrived at similar formulas, including a 4/3 factor for the relation of mass to energy. However, their work was focused on electromagnetic energy, which, as we know today, only represents a small part of the entire energy within matter. So it was Einstein who was the first to ascribe this relation to all forms of energy, and to understand the connection of mass-energy equivalence with the relativity principle. Early reception. First assessments. Walter Kaufmann, 1905-1906, was probably the first who referred to Einstein's work. He compared the theories of Lorentz and Einstein, and, although he said Einstein's method is to be preferred, he argued that both theories are observationally equivalent. Therefore he spoke of the relativity principle as the Lorentz-Einsteinian basic assumption. Shortly afterwards, Max Planck, 1906, was the first who publicly defended the theory, and interested his students, Max von Laue and Kurt von Mosengeil, in this formulation. He described Einstein's theory as a generalization of Lorentz's theory, and to this Lorentz-Einstein theory he gave the name relative theory, while Alfred Butcherer changed Planck's nomenclature into the now common theory of relativity. On the other hand, Einstein himself and many others continued to refer simply to the new method as the relativity principle. And in an important overview article on the relativity principle, 1908, Einstein described SR as a union of Lorentz's theory and the relativity principle, including the fundamental assumption that Lorentz's local time can be described as real time. Yet, Poincaré's contributions were rarely mentioned in the first years after 1905. All of those expressions, Lorentz-Einstein theory, relativity principle, relativity theory, were used by different physicists alternately in the next years. Kaufmann-Butcherer experiments. Kaufmann, 1905-1906, announced the results of his new experiments on the charge-to-mass ratio, i.e. the velocity dependence of mass. They represented, in his opinion, a clear refutation of the relativity principle and the Lorentz-Einstein theory, and a confirmation of Abraham's theory. For some years Kaufmann's experiments represented a weighty objection against the relativity principle, although it was criticized by Planck and Adolf Bestelmeyer, 1906. Following Kaufmann, other physicists, like Alfred Butcherer, 1908, and Günther Neumann, 1914, also examined the velocity dependence of mass, and this time it was thought that the Lorentz-Einstein theory and the relativity principle were confirmed, and Abraham's theory disproved. However, it was later pointed out that the Kaufmann-Butcherer-Neumann experiments only showed a qualitative mass increase of moving electrons, but they were not precise enough to distinguish between the models of Lorentz-Einstein and Abraham. So it continued until 1940, when experiments of this kind were repeated with sufficient accuracy for confirming the Lorentz-Einstein formula. However, this problem occurred only with this kind of experiment. The investigations of the fine structure of the hydrogen lines already in 1917 provided a clear confirmation of the Lorentz-Einstein formula and the refutation of Abraham's theory. Relativistic momentum and mass. Max Planck. Planck, 1906, defined the relativistic momentum and gave the correct values for the longitudinal and transverse mass by correcting a slight mistake of the expression given by Einstein in 1905. Planck's expressions were in principle equivalent to those used by Lorentz in 1899. Based on the work of Planck, the concept of relativistic mass was developed by Gilbert Newton Lewis and Richard C. Tolman, 1908-1909, by defining mass as the ratio of momentum to velocity. So the older definition of longitudinal and transverse mass, in which mass was defined as the ratio of force to acceleration, became superfluous. Finally, Tolman, 1912, interpreted relativistic mass simply as the mass of the body. However, many modern textbooks on relativity don't use the concept of relativistic mass anymore, and mass in special relativity is considered as an invariant quantity. Mass and energy. Einstein, 1906, showed that the inertia of energy, mass-energy equivalence, is a necessary and sufficient condition for the conservation of the center of mass theorem. On that occasion, he noted that the formal mathematical content of Poincaré paper on the center of mass, 1900b, and his own paper were mainly the same, although the physical interpretation was different in light of relativity. Kurt von Mosengeil, 1906, by extending Hayes-Rohl's calculation of black-body radiation in a cavity, derived the same expression for the additional mass of a body due to electromagnetic radiation as Hayes-Rohl. Hayes-Rohl's idea was that the mass of bodies included a contribution from the electromagnetic field. He imagined a body as a cavity containing light. His relationship between mass and energy, like all other pre-Einstein ones, contained incorrect numerical prefactors. See electromagnetic mass. Eventually Planck, 1907, derived the mass-energy equivalence in general within the framework of special relativity, including the binding forces within matter. He acknowledged the priority of Einstein's 1905 work on, but Planck judged his own approach as more general than Einstein's. Experiments by Fizeau and Sagnac. As it was explained above, already in 1895 Lorentz succeeded in deriving Fresnel's dragging coefficient to first order of V/c, and the Fizeau experiment, by using the electromagnetic theory and the concept of local time. After first attempts by Jacob Laub, 1907, to create a relativistic optics of moving bodies, it was Max von Laue, 1907, who derived the coefficient for terms of all orders, by using the collinear case of the relativistic velocity addition law. In addition, Laue's calculation was much simpler than the complicated methods used by Lorentz. In 1911 Laue also discussed a situation where on a platform a beam of light is split, and the two beams are made to follow a trajectory in opposite directions. On return to the point of entry, the light is allowed to exit the platform in such a way that an interference pattern is obtained. Laue calculated a displacement of the interference pattern if the platform is in rotation. Because the speed of light is independent of the velocity of the source, so one beam has covered less distance than the other beam. An experiment of this kind was performed by Georges Sagnac in 1913, who actually measured a displacement of the interference pattern, Sagnac effect. While Sagnac himself concluded that his theory confirmed the theory of an ether at rest, Laue's earlier calculation showed that it is compatible with special relativity as well, because in both theories the speed of light is independent of the velocity of the source. This effect can be understood as the electromagnetic counterpart of the mechanics of rotation, for example an analogy to a Foucault pendulum. Already in 1909-11, Franz Harris, 1912, performed an experiment which can be considered as a synthesis of the experiments of Fizeau and Sagnac. He tried to measure the dragging coefficient within glass. Contrary to Fizeau, he used a rotating device, so he found the same effect as Sagnac. While Horace himself misunderstood the meaning of the result, it was shown by Lau that the theoretical explanation of Horace's experiment is in accordance with the Sagnac effect. Eventually, the Michelson-Gale-Pearson experiment, 1925, a variation of the Sagnac experiment, indicated the angular velocity of the Earth itself in accordance with special relativity and arresting ether. Relativity of simultaneity. The first derivations of relativity of simultaneity by synchronization with light signals were also simplified. Daniel Frost Comstock, 1910, placed an observer in the middle between two clocks A and B. From this observer a signal is sent to both clocks, and in the frame in which A and B are at rest, they synchronously start to run. But from the perspective of a system in which A and B are moving, clock B is first set in motion, and then comes clock A, so the clocks are not synchronized. Also Einstein, 1917, created a model with an observer in the middle between A and B. However, in his description two signals are sent from A and B to the observer. From the perspective of the frame, in which A and B are at rest, the signals are sent at the same time, and the observer is hastening towards the beam of light coming from B, whilst he is riding on ahead of the beam of light coming from A. Hence the observer will see the beam of light emitted from B earlier than he will see that emitted from A. Observers who take the railway train as their reference body must therefore come to the conclusion that the lightning flash B took place earlier than the lightning flash A. Space-time physics. Minkowski spacetime. Hermann Minkowski. Poincaré's attempt of a four-dimensional reformulation of the new mechanics was not continued by himself, so it was Hermann Minkowski, 1907, who worked out the consequences of that notion. Other contributions were made by Roberto Marcolongo, 1906, and Richard Hargreaves, 1908. This was based on the work of many mathematicians of the 19th century, like Arthur Cayley, Felix Klein, or William Kingdon Clifford, who contributed to group theory, invariant theory, and projective geometry. Using similar methods, Minkowski succeeded in formulating a geometrical interpretation of the Lorentz transformation. He completed, for example, the concept of four vectors. He created the Minkowski diagram for the depiction of spacetime. He was the first to use expressions like world line, proper time, Lorentz invariance/covariance, etc., and most notably he presented a four-dimensional formulation of electrodynamics. Similar to Poincaré, he tried to formulate a Lorentz invariant law of gravity, but that work was subsequently superseded by Einstein's elaborations on gravitation. In 1907, Minkowski named four predecessors, who contributed to the formulation of the relativity principle: Lorentz, Einstein, Poincaré, and Planck. And in his famous lecture Space and Time, 1908, he mentioned Voigt, Lorentz, and Einstein. Minkowski himself considered Einstein's theory as a generalization of Lorentz's, and credited Einstein for completely stating the relativity of time, but he criticized his predecessors for not fully developing the relativity of space. However, modern historians of science argue that Minkowski's claim for priority was unjustified, because Minkowski, like Wien or Abraham, adhered to the electromagnetic world picture, and apparently didn't fully understand the difference between Lorentz's electron theory and Einstein's kinematics. In 1908, Einstein and Lau rejected the four-dimensional electrodynamics of Minkowski as too complicated and published a more elementary non-four-dimensional derivation of the basic equations for moving bodies. But it was Minkowski's formalism which showed that special relativity is a complete and consistent theory, and served as a basis for further development of relativity. Eventually, Einstein, 1912, agreed on the importance of Minkowski's spacetime formalism, and used it for his work on the foundations of general relativity. Today special relativity is seen as an application of linear algebra, but at the time special relativity was being developed the field of linear algebra was still in its infancy. There were no textbooks on linear algebra as modern vector space and transformation theory, and the matrix notation of Arthur Cayley, that unifies the subject, had not yet come into widespread use. Cayley's matrix calculus notation was used by Minkowski, 1908, in formulating relativistic electrodynamics, even though it was later replaced by Sommerfeld using vector notation. In retrospect, we can see that the Lorentz transformations are equivalent to hyperbolic rotations. Vector notation and closed systems. Minkowski's spacetime formalism was quickly accepted and further developed. For example, Arnold Sommerfeld, 1910, replaced Minkowski's matrix notation by an elegant vector notation and coined the terms 4-vector and 6-vector. He also introduced a trigonometric formulation of the relativistic velocity addition rule, which according to Sommerfeld removes much of the strangeness of that concept. Other important contributions were made by Lau, 1911-1913, who used the spacetime formalism to create a relativistic theory of deformable bodies, and an elementary particle theory. 87. He extended Minkowski's expressions for electromagnetic processes to all possible forces, and thereby clarified the concept of mass-energy equivalence. Lau also showed that non-electrical forces are needed to ensure the proper Lorentz transformation properties, and for the stability of matter he could show that the Poincaré stresses as mentioned above are a natural consequence of relativity theory so that the electron be a closed system. Lorentz transformation without second postulate. There were some attempts to derive the Lorentz transformation without the postulate of the constancy of the speed of light. Vladimir Ignatowski, 1910, for example, used for this purpose the principle of relativity, B, and homogeneity and isotropy of space, C, the requirement of reciprocity. Philip Frank and Hermann Roth, 1911, argued that this derivation is incomplete and needs additional assumptions. Their own calculation was based on the assumptions that A, the Lorentz transformation forms a homogeneous linear group, B, when changing frames, only the sign of the relative speed changes, C, length contraction solely depends on the relative speed. However, according to Pauli and Miller, such models were insufficient to identify the invariant speed in their transformation with the speed of light. For example, Ignatowski was forced to recourse to electrodynamics to include the speed of light. So Pauli and others argued that both postulates are needed to derive the Lorentz transformation. However, until today, others continue the attempts to derive special relativity without the light postulate. Non-Euclidean formulations without imaginary time coordinate. It was noted by Minkowski, 1907, that his spacetime formalism represents a four-dimensional non-Euclidean manifold, but in order to emphasize the formal similarity to the more familiar Euclidean geometry, Minkowski noted that the time coordinate could be treated as imaginary. This was just a way of representing a non-Euclidean metric, while emphasizing the formal similarity to a Euclidean metric. However, subsequent writers have dispensed with the imaginary time coordinate, and simply written the metric in explicitly non-Euclidean form, i.e., with a negative signature. Sommerfeld, 1910, gave a trigonometric formulation of velocities. Vladimir Varier K. 1912, emphasized the similarity of this formulation to Bolyai-Lobachevskian hyperbolic geometry, and tried to reformulate relativity using that non-Euclidean geometry. Alfred Drob, 1911, introduced the concept of rapidity as a hyperbolic angle to characterize frame velocity. Edwin Bidwell Wilson and Gilbert N. Lewis, 1912, introduced a vector notation for spacetime. Emil Borel, 1913, derived the kinematic basis of Thomas precession. Felix Klein, 1910, and Ludwig Silberstein, 1914, employed such methods as well. One historian argues that the non-Euclidean style had little to show in the way of creative power of discovery, but it offered notational advantages in some cases, particularly in the law of velocity addition. So in the years before World War I, the acceptance of the non-Euclidean style was approximately equal to that of the initial space-time formalism, and it continued to be employed in relativity textbooks of the 20th century. Time dilation and twin paradox. Einstein, 1907, proposed a method for detecting the transverse Doppler effect as a direct consequence of time dilation. And in fact, that effect was measured in 1938 by Herbert T. Ives and G.R. Stilwell, Ives-Stilwell experiment. And Lewis and Tolman, 1909, described the reciprocity of time dilation by using two light clocks A and B traveling with a certain relative velocity to each other. The clocks consist of two plane mirrors parallel to one another and to the line of motion. Between the mirrors a light signal is bouncing. And for the observer resting in the same reference frame as A, the period of clock A is the distance between the mirrors divided by the speed of light. But if the observer looks at clock B, he sees that within that clock the signal traces out a longer, angled path, thus clock B is slower than A. However, for the observer moving alongside with B the situation is completely in reverse. Clock B is faster and A is slower. Also Lorentz, 1910-1912, discussed the reciprocity of time dilation, and analyzed a clock paradox which apparently occurs as a consequence of the reciprocity of time dilation. Lorentz showed that there is no paradox, if one considers that in one system only one clock is used, while in the other system two clocks are necessary. So the relativity of simultaneity has to be considered as well. Max von Laue. A similar situation was created by Paul Langevin in 1911 with what was later called the twin paradox, where he replaced the clocks by persons. Langevin never used the word twins, but his description contained all other features of the paradox. Langevin solved the paradox by alluding to the fact that one twin accelerates and changes direction, so Langevin could show that the symmetry is broken and the accelerated twin is younger. However, Langevin himself interpreted this as a hint to the existence of an ether. Although Langvin's explanation is used in principle until today, his deductions regarding the ether were not accepted. Laue, 1913, pointed out that the acceleration can be made arbitrarily small in relation to the inertial motion of the twin. So it is much more important that one twin travels within two inertial frames during his journey, while the other twin remains in one frame. Laue was also the first to visualize the situation using Minkowski's space-time formalism. He demonstrated how the world lines of inertially moving bodies maximize the proper time elapsed between two events. Acceleration. Einstein, 1908, tried, as a preliminary in the framework of special relativity, also to include accelerated frames within the relativity principle. In the course of this attempt he recognized that for any single moment of acceleration of a body one can define an inertial reference frame, in which the accelerated body is temporarily at rest. It follows that in accelerated frames defined in this way, the application of the constancy of the speed of light to define simultaneity is restricted to small localities. However, the equivalence principle that was used by Einstein in the course of that investigation, which expresses the equality of inertial and gravitational mass, and the equivalence of accelerated frames and homogeneous gravitational fields, transcended the limits of special relativity, and resulted in the formulation of general relativity. Nearly simultaneously with Einstein, also Minkowski, 1908, considered the special case of uniform accelerations within the framework of his space-time formalism. He recognized that the world line of such an accelerated body corresponds to a hyperbola. This notion was further developed by Born, 1909, and Sommerfeld, 1910, with Born introducing the expression hyperbolic motion. He noted that uniform acceleration can be used as an approximation for any form of acceleration within special relativity. In addition, Harry Bateman and Ebenezer Cunningham, 1910, showed that Maxwell's equations are invariant under a much wider group of transformation than the Lorentz group, i.e., the spherical wave transformations being a form of conformal transformations. Under those transformations, the equations preserve their form for some types of accelerated motions. A general covariant formulation of electrodynamics in Minkowski space was eventually given by Friedrich Adler, 1912, whereby his formulation is also valid for general relativity. Concerning the further development of the description of accelerated motion in special relativity, the works by Langevin and others for rotating frames, Born coordinates, and by Wolfgang Rendler and others for uniform accelerated frames, Rendler coordinates, must be mentioned. Rigid bodies and Ehrenfest paradox. Einstein, 1907b, discussed the question of whether, in rigid bodies, as well as in all other cases, the velocity of information can exceed the speed of light, and explain that information could be transmitted under these circumstances into the past, thus causality would be violated. Since this contravenes radically against every experience, superluminal velocities are thought impossible. He added that the dynamics of the rigid body must be created in the framework of SR eventually. Max Born, 1909, in the course of his above-mentioned work concerning accelerated motion, tried to include the concept of rigid bodies into SR. However, Paul Ehrenfest, 1909, showed that Born's concept lead the so-called Ehrenfest paradox, in which, due to length contraction, the circumference of a rotating disk is shortened while the radius stays the same. This question was also considered by Gustav Herglotz, 1910, Fritz Nether, 1910, and von Lau, 1911. It was recognized by Lau that the classic concept is not applicable in SR, since a rigid body possesses infinitely many degrees of freedom. Yet, while Born's definition was not applicable on rigid bodies, it was very useful in describing rigid motions of bodies. In connection to the Ehrenfest paradox, it was also discussed, by Vladimir Variake, and others, whether length contraction is real or apparent and whether there is a difference between the dynamic contraction of Lorentz and the kinematic contraction of Einstein. However, it was rather a dispute over words because, as Einstein said, the kinematic length contraction is apparent for an co-moving observer, but for an observer at rest it is real, and the consequences are measurable. Acceptance of special relativity. Eventually, by about 1911, most mathematicians and theoretical physicists accepted the results of special relativity. For example, Planck, in 1909, compared the implications of the modern relativity principle, especially Einstein's relativity of time, with the revolution by the Copernican system. As a result, the fundamental difference between the dynamic approach of Lorentz and the kinematic one of Einstein was pointed out, and the term Lorentz-Einstein theory was not used anymore. Only a few theoretical physicists, like Lorentz, Poincaré, Abraham, or Langevin, still believed in the existence of an ether in any form. Another important reason for accepting special relativity was the extension of Minkowski's spacetime formalism, around 1910-1913. So in 1912 Wilhelm Wien recommended both Lorentz and Einstein for the Nobel Prize in Physics, even though this prize was never awarded for special relativity. After formulating Gr. Einstein in 1915, for the first time, used the expression special theory of relativity to distinguish between the theories. Relativistic theories. Gravitation. The first attempt to formulate a relativistic theory of gravitation was undertaken by Poincaré, 1905. He tried to modify Newton's law of gravitation so that it assumes a Lorentz covariant form. He noted that there were many possibilities for a relativistic law, and he discussed two of them. It was shown by Poincaré that the argument of Pierre-Simon Laplace, who argued that the speed of gravity is many times faster than the speed of light, is not valid within a relativistic theory. That is, in a relativistic theory of gravitation, planetary orbits are stable even when the speed of gravity is equal to that of light. Similar models as that of Poincaré were discussed by Minkowski, 1907b, and Sommerfeld, 1910. However, it was shown by Abraham, 1912, that those models belong to the class of vector theories of gravitation. The fundamental defect of those theories is that they implicitly contain a negative value for the gravitational energy in the vicinity of matter, which would violate the energy principle. As an alternative, Abraham, 1912, and Gustav Mott, 1913, proposed different scalar theories of gravitation. While Mott never formulated his theory in a consistent way, Abraham completely gave up the concept of Lorentz covariance, even locally, and therefore it was irreconcilable with relativity. In addition, all of those models violated the equivalence principle, and Einstein argued that it is impossible to formulate a theory which is both Lorentz covariant and satisfies the equivalence principle. However, Gunnar Nordström, 1912-1913, was able to create a model which fulfilled both conditions. This was achieved by making both the gravitational and the inertial mass dependent on the gravitational potential. Nordström's theory of gravitation was remarkable because it was shown by Einstein and Adrian Fokker, 1914, that in this model gravitation can be completely described in terms of space-time curvature. Although Nordström's theory is without contradiction, from Einstein's point of view a fundamental problem persisted. It doesn't fulfill the important condition of general covariance, as in this theory preferred frames of reference can still be formulated. So contrary to those scalar theories, Einstein, 1911-1915, developed a tensor theory, i.e. general relativity, which fulfills both the equivalence principle and general covariance. As a consequence, the notion of a complete special relativistic theory of gravitation had to be given up, as in general relativity the constancy of light speed and Lorentz covariance is only locally valid. The decision between those models was brought about by Einstein, when he was able to exactly derive the perihelion precession of Mercury, while the other theories gave erroneous results. In addition, Einstein's theory was the only theory which gave the correct value for the deflection of light near the Sun. Quantum field theory. The need to put together relativity and quantum mechanics was one of the major motivations in the development of quantum field theory. Pascual Jordan and Wolfgang Pauli showed in 1928 that quantum fields could be made to be relativistic, and Paul Dirac produced the Dirac equation for electrons, and in so doing predicted the existence of antimatter. Many other domains have since been reformulated with relativistic treatments: relativistic thermodynamics, relativistic statistical mechanics, relativistic hydrodynamics, relativistic quantum chemistry, relativistic heat conduction, etc. Experimental evidence. Important early experiments confirming special relativity, as mentioned above, were the Fizeau experiment, the Michelson-Morley experiment, the Kaufmann-Butcherer-Newman experiments, the Troughton-Noble experiment, the experiments of Rayleigh and Brace, and the Troughton-Rankine experiment. In the 1920s, a series of Michelson-Morley type experiments were conducted, confirming relativity to even higher precision than the original experiment. Another type of interferometer experiment was the Kennedy-Thorndike experiment in 1932, by which the independence of the speed of light on the apparatus velocity was confirmed. Also, time dilation was directly measured in the Ives-Stilwell experiment in 1938, and by measuring the decay rates of moving particles in 1940. All of those experiments have been repeated several times with increased precision. In addition, that the speed of light is unreachable for massive bodies was measured in many tests of relativistic energy and momentum. Therefore, knowledge of those relativistic effects is required in the construction of particle accelerators. Many other tests of special relativity have been conducted, testing possible violations of Lorentz invariance in some variants of quantum gravity. However, no sign of anisotropy of the speed of light has been found even at the 1017 level, and some experiments even ruled out Lorentz violations at the 1040 level. See modern searches for Lorentz violation. Priority. Some claim that Poincaré and Lorentz, not Einstein, are the true founders of special relativity. For more, see the article on relativity priority dispute. Criticisms. Some criticize special relativity for various reasons, such as lack of empirical evidence, internal inconsistencies, rejection of mathematical physics per se, or philosophical reasons. Although there still are critics of relativity outside the scientific mainstream, the overwhelming majority of scientists agree that special relativity has been verified in many different ways, and there are no inconsistencies within the theory.